But that's all right, Jamie. You'll keep your job and stuff. It's slightly intimidating to be here. First of all, to go up against Jesse Norman. I was looking at the schedule. I was about to wander on over and listen to Jesse Norman and then realized I couldn't because I was giving this talk. So I thank you all for coming. I promised not to sing, and she promised me today that she would not try to explain Einstein's relativity. I do also want to acknowledge one person in the audience who truly helped me on this book quite a bit, and you've probably heard him recently, but Arthur I. Miller, who did Einstein Picasso, also wrote a great book on black holes, Empire of the Stars. I think he's speaking tomorrow morning at Maroon Bells, and if you still need a ticket, even though it's sold out, you can talk to Jamie and she'll print an extra ticket for you to go to it. I did say to Arthur a moment ago that if after explaining a couple of these theories twice you still don't get it, I'm going to make him explain some of them. But the good news for those of us, Arthur is a philosopher of science and a good physicist as well, but for those of us who aren't geniuses in physics but feel that we want to capture the beauty and creativity of an Einstein, that was the purpose of this book. Just as I'm not a great singer, but I can appreciate when Jesse Norman does spirituals or for that matter opera, and just as I'm not a visual artist, but I can appreciate what Picasso does, I think those of us who are not scientists should get back in the habit, as Benjamin Franklin did in his century, or people have done in all previous centuries, is appreciate the creativity and beauty of science. People say, oh, it's so good you're writing about science because in this new century, we're going to have to deal with so much science like stem cell research and global warming. And yes, that's a reason for us to appreciate the scientific way of thinking, of testing hypotheses and that sort of thing. However, I believe we should understand science not just so we'll be good at figuring out how to vote when it comes to stem cell research, but because science is a thing of beauty and the pursuit of science is a thing of creativity. And Einstein making creative leaps is just like a Picasso or a Joyce or a Proust or a Faulkner making creative leaps. And people who are my friends would never go around admitting that they didn't know the difference between Hamlet and Macbeth, but they might brag that they know nothing about the difference between relativity theory and the uncertainty principle. And I just think we should all try to understand the beauty of science, the creativity, the imagination that comes with science, as well as we would try to do it with Shakespeare. And we can love Hamlet without fully understanding whether Hamlet loves Ophelia. We can love Einstein without fully understanding the tensor calculus that underlies general relativity. And the good news for those of us who will never fully understand Riemannian geometry and the tensor calculus that underlies relativity is for us to remember that Einstein was no Einstein when he was a kid. He was very slow in learning how to talk, so slow that they dubbed him the dopey one in the family. And they even consulted a doctor to explain why he was having such slow verbal learning abilities. But I do think that his slow verbal learning abilities made him the patron saint of distracted school kids everywhere, but it also helped him think more imaginatively. Because as he always said, imagination, fantasy, creativity is more important than knowledge. One of the things he said is that he developed so slowly as a child that he started wondering about things after most people had already passed on, wondering about why time moves. Does it move the same for everybody? What is space? So, things like that. When he was a very young kid, his father gave him a compass at age 5. And he sat there for days on end, he recalled, over and over again, he would recall the tail of the compass. And watching as that needle pointed north. And it would say, it would make him have chills as he sat up at night, wondering about the unseen forces of nature, that there were force fields in between objects, unseen forces that guided things and caused that compass needle to twitch north. From age 5 until his deathbed, he's still writing field theories, trying to explain the forces of nature. Now, you and I probably remember getting a compass when we were kids. And you walk outside and it points north, you go, oh, cool, it points north. And about 90 seconds later, you're on to something else. You see a dead squirrel, and say, oh, cool, a dead squirrel. But what made Einstein special is that those things that you and I might pass over, that there's a force field making that compass needle point north, he kept focusing on that, wondering about that, being surprised by that his whole life. The other thing that gets him kicked out of school as a kid, and another headmaster amuses us by saying this Einstein will never amount to much, is that he was always very rebellious. He questioned authority at all times. One headmaster says, your undermining of authority is why I need you to leave this class. You're undermining the other pupil's authority, sense of authority in me. And he said that sense of rebelliousness, he was always suspicious of authority. It never left him. A foolish faith in authority is the worst enemy of truth. Now, one of the things that's not true about Einstein, unfortunately, is that he flunked math as a kid. You kind of want it to be true. In fact, if you Google Einstein failed math, you get 66,000 websites saying things like, as everybody knows, Einstein failed math as a kid, so maybe there's hope for me. But it's not true. There's Einstein, there's his grades in math, the highest possible grades. And he was not very good in his language, his verbal ability, but he did fine in math. And it was because of that thing I talked about earlier, that creative, imaginative ability to visualize things. He was able always to visualize even mathematical equations, do what he called visual thought experiments involving them. That's what you and I call daydreaming. If you're Einstein, you get to call it a thought experiment. But he would understand that a mathematical equation was just the good Lord's brushstroke for painting something in reality. There was an underlying reality to a mathematical equation. Most of you know my daughter Betsy. I was helping her a few weeks ago with her math homework, and she had an equation that she had multiplied and gotten the answer wrong. And she said, "Why is this wrong?" I said, "Well, just look at the equation. It's got to swoop upward like that. It's got to move up real fast, exponentially." She said, "What do you mean?" I said, "Well, an equation is simply a representation of an underlying reality. You should visualize the underlying reality when you look at an equation." And she said, "Oh, no, Dad, that's not the way they teach math these days." But in some ways, that's a shame, because math should be taught as a creative endeavor, an endeavor that has a visual, imaginative component to it. Now, Albert Einstein, believe it or not, Linda, was actually smarter than my daughter at age 16. Yeah. And at age 16, he is wondering and visualizing Maxwell's equations. Now, Maxwell's equations, of course, are just a set of equations that describe an electromagnetic wave or a light wave. And sort of discovered, right? James Clerk Maxwell died the year Einstein was born. And Einstein, just as I think Newton dies the year Newton is born the year Galileo dies, that always affected Einstein. And he thought there was something somewhat, if not spiritual, at least significant in the fact that he is born the year Maxwell dies, and he's trying to, the rest of his life, understand field theory, field equations, including Maxwell's equations for a light wave. One of the interesting things about Maxwell's equations, especially if you're Einstein as a 16-year-old and you can visualize it, is that no matter how fast you're traveling, whatever your frame of reference, Maxwell's equations say that the light wave always travels at a constant speed, about 186,000 miles per second or so, the speed of light, the constant speed of light. No matter what you're doing, no matter how you observe the light wave, whatever your moving frame of reference, Maxwell's equations say that the wave always has to travel at the same speed. So Einstein, as a 16-year-old, does his thought experiment. He says, well, what if you catch up with the wave? What if you're moving so fast that you're riding right alongside the light wave? Wouldn't it be stationary compared to you? Couldn't you catch up with it? But Maxwell's equations don't allow for that. And so he said, for days on end, I would walk around with my palms sweating. This gave me such anxiety. Now, I don't know about you, but it caused me to think, what was causing my palms to sweat at age 16? And it wasn't Maxwell's equations. But that's why he's Einstein and we're not. Basically, he runs away from the rigid German schools, the school system. sort of half gets kicked out. As I said, the headmaster says that you're undermining the respect for me. I'd rather you leave the school. He runs away at Christmas time, runs away to Italy and then to Switzerland, and he applies for admission in what is basically the second best college in Zurich at the time, the Zurich Polytech. And he doesn't get in. Now, those of us with kids applying to college, I've always wanted to meet the admissions director of the Zurich Polytech, who had rejected Albert Einstein for having not done well on the verbal and languages part of his exams. But fortunately, Einstein does get in his second time around, goes to the Zurich Polytech, does moderately well at the Zurich Polytech, but he's able to tick off all of the professors there with his disrespect for authority. Hermann Minkowski, the great math teacher there, Einstein doesn't like the way he teaches it. It's by rote. So Einstein doesn't even go to math class. He has his friend Marcel Grossman go to math class for him and take notes for him, causing Minkowski to pronounce later on that Einstein was a lazy dog. Now, those of us who've ever had professors say that about us, and I had one like that who just totally didn't like me, it's always good. You always have this fantasy, which I never quite fulfilled, but Einstein did. Einstein comes up with the theory of relativity. It is Minkowski who has to write the underlying mathematics for the special theory, the 4 dimensions of space-time, saying he never really thought Einstein would have it in it. Heinrich Weber is the physics professor there. He doesn't even teach Maxwell's equations because they're too newfangled. When Einstein explains his dilemma about Maxwell's equations, Weber says, well, my course doesn't really go up that far. Einstein quits calling him Herr Professor and starts calling him Herr Weber, which Weber considers a sign of disrespect and basically has little to do with Einstein after that. Another instructor was Pernet, the lab instructor. Einstein was never very good in the lab. He was never a very good experimentalist, which is why he had to become a theorist, I guess. But at one point, he throws away a set of instructions for doing the lab report that's supposed to do in Pernet's class, ends up blowing up the equipment, and Pernet puts him on academic probation. So anyway, thus it is that Einstein is the only graduate of the 1900 class of the Zurich Polytech who can't get any recommendations from any professors for a job. He can't get any academic job. He can't get an assistant professorship, doctoral fellowships. He's spamming Europe with letters, job applications, even to teach in high school. And none of the he realizes that Weber in particular is giving him bad recommendations. He can't get it. So he wanders around for 2 years, basically unemployed, trying to find tutoring jobs and stuff, until finally Einstein gets a job as a third-class examiner in the patent office in Bern, Switzerland, the Swiss patent office. A third-class examiner because the qualifications to be a second-class or first-class examiner, including it meant you had to have a doctorate. His doctoral dissertation had been rejected, I think, twice. It's a little unclear, but clearly he keeps getting his fee back, at least we know, because the people in Zurich wouldn't give him a doctorate. So he's a third-class examiner in the patent office, a window in the Post and Telegraph building on the 3rd floor. Not too far from the office is the great Bern clock tower, for those of you who have been in Bern. Beautiful 11th century clock tower. The trains actually zip by underneath the clock tower. And lest we feel sorry for Einstein, sitting there 6 days a week on a stool, examining patent applications, trying to write in his spare time, I think it was probably best for him. And I should give credit where it's due. It's actually an author's book, but certainly in a book by Peter Gallison called Einstein's Clocks, Poincaré's Maps. Looking at the patent applications that Einstein is doing, one of the things that's happening at the time is that in Switzerland, they've gone to standard time zones. And the Swiss, who are kind of Swiss, they're obsessive about making sure the clocks are synchronized. So there's 72 patent applications for the synchronizing of clocks in Switzerland. And there he is watching the trains going in the station. And one of the things about the patent applications about the synchronizing of clocks is that you send a signal between 2 very distant clocks in order to synchronize them, and the signal travels at the speed of light, whether it's a radio signal, a light signal, electric signal, whatever. So there he is thinking about all of these things as a patent examiner. He's got his friends, the Olympia Academy and other friends. They discuss philosophy. They're reading Hume. And fortunately, this is Einstein here. This guy here, Conrad, goes away. Oh, gosh, I see another physicist who helped me, Lawrence Krauss. So I'm going to skip all the physics here in this lecture. I usually can wing it without people who know it better than I do, sort of say, shaking their heads. But anyway, Conrad goes away for a few weeks. And thus, we're so lucky we have one of the coolest letters in the history of science. Because Conrad doesn't write Einstein, and Einstein is mad. So he sends a letter to Conrad that starts, "You frozen whale, you canned piece of soul, you haven't written me, and so I'm going to send you a letter that's simply filled with inconsequential babble. But if you write me," he says, "I promise to send you 4 papers I've been working on in my spare time in return." This is 1905, the miracle year. May of 1905, he's sitting there in the patent office, and in his spare time, he's working on 4 papers. It's only when you get to the second paragraph of that letter, the second paragraph, that you realize, okay, this is not totally inconsequential babble. He says the first paper deals with the energy properties of light and is actually very revolutionary. Indeed, it might have been the most revolutionary scientific paper written in the 20th century. It says, to boil it down to its essence, that light is not only a wave, it's a particle. What he had done is he had looked at an equation that Max Planck had done to explain radiation. Max Planck, up until that very week, probably the greatest scientist in all of Europe. He's about to be surpassed by a third-class patent clerk. But up until that, Max Planck had written equations that explained radiation coming off of a piece of heated metal. But Max Planck did, to put in a little mathematical contrivance to make the curve work right. And it was called Planck's constant, a tiny little mathematical thing. Nobody quite knew what Planck's constant was. Planck himself calls it just a mathematical contrivance. Albert Einstein, sitting at his desk in the patent office, able to visualize equations, realizes that light is both wave and particle, called quanta, and that's what the mathematical contrivance sort of represents. He says the second paper deals with the true size of atoms and molecules, he says in the letter to Conrad. Back then, probably a majority of scientists were not sure that atoms and molecules really existed. They thought maybe it was just sort of a theory, you couldn't really prove it. Here's the patent clerk not only saying they exist, but coming up with a way to determine their size. He realizes that even though this is somewhat controversial, it's the simplest of the 4 papers that he's written, so he uses it for his latest attempt to get a doctoral dissertation accepted. The third paper, he says, explains Brownian motion, which is why tiny little particles jiggle in water. And then he says the 4th paper is only in rough draft at this point, but it deals with a modification of the theory of time. Well, that's not inconsequential babble. Obviously, it's the special theory of relativity. What he doesn't tell Conrad in the letter, because he hasn't thought of it yet, but he'll think of it right after he sends a letter, sends off the draft of that paper, and right a few weeks later, it occurs to him that if that paper is right and what he's done that year is right, there's an equivalence that exists between energy and mass. And so in the intervening few weeks when he's on vacation in Serbia, he comes up with the most famous equation in all of physics. E equals mc squared. That energy has a relationship to mass that involves the square of the speed of light. Now, relativity is a very simple concept. It simply says, whatever your constant velocity motion, whatever frame of reference you are, you can't sort of be privileged. You can't say, I'm at rest and you're at motion. All laws of physics apply equally in any frame of reference that's in constant velocity. Imagine 2 people in a spaceship gliding by. Each can bounce a ball. Each can heat up a cup of tea in a microwave. Each can do anything they want. You can throw a ball up and down, whatever. And if you're gliding along, you can't sort of say, I'm at rest, you're at motion. all frames of reference are equal. Even here, you think you're sitting in the door hosier building totally at rest. You can look and see a plane up there landing at Aspen Airport, gliding at a constant velocity, let us say. You can say, well, I'm at rest, the plane's moving. But no, we're spinning around the sun, where sun's going around the galaxy is doing God knows what. Actually, Arthur knows what the galaxies are doing. I've never figured out what galaxies do. And, the person on the plane could say, no, the Earth is in motion and I'm still and just moving by. So that's all the principle of relativity says. The problem with the principle of relativity is it seems, if you're a 16-year-old doing that thought experiment about Maxwell's equations, well, how does that affect the speed of light? Couldn't you catch up with the speed of light? Does Maxwell's equations apply the same way to any body in constant velocity motion? Einstein couldn't figure out. Nobody could figure out. Michelson and Morley are doing all sorts of experiments. No matter how you're moving towards the sun, away from the sun, the Earth is moving, whatever. Speed of light is always constant. Nobody can quite put it all together. Einstein tells his other friend, Michele Besso, I can't get it. I can't get it. I'm giving up, he says at one point. And then that week in May that he's written Conrad the letter, Einstein does what he calls the step. Sunny day in May, he says, walking with Michele Besso. Michele Besso is an engineer. He had gotten a job at the patent office, even more of a ne'er-do-well than Einstein. He says to Besso, I've got it. I've got it. He explains it to Besso the next day. And it's simply, all Einstein's great step is that, what do you mean by something being simultaneous? Now, once again, you and I, because we're so smart, unlike Einstein, we don't pause to think, what does it mean to be simultaneous, right? You say simultaneous, that just means it happens at the same time. If you're Einstein, if you're a patent examiner, you say, well, how do we know? How can we have an operational definition that defines what is simultaneous? If you heard David Bradley do the introduction to this, he did his version of this. But to define simultaneity for a patent clerk, it means, well, suppose two very distant events happen, and somebody is exactly halfway in between those two events. The light from both events hits that person at the same time. That person would say the two events are simultaneous, right? That's a good operational definition of simultaneous. Einstein says, and this is a drawing he uses in one of, or not exactly like this, but it's a drawing like this. He says, imagine lightning striking both ends of a moving train. He says, suppose there's a person standing on the platform halfway in between. That person sees the light from each lightning strike hitting him at the exact same time. That person says the lightning strikes are simultaneous. But imagine there's a woman on the train, and the train is a thought experiment, moving really, really fast. She's inched ahead a little bit. And the time it takes the light to get there, because the speed of light is finite, even though it's fast, and the time it takes to get there, she's a little bit further ahead. She sees the light from the lightning strike ahead first. She says they're not simultaneous. She says, no, the one in front happened first, because the light from the one in front gets to her first. He could say, well, you're wrong. I'm at rest. I'm on the platform. You're the one who's moving. Principle of relativity says there's no preferred reference frame. Neither one of them is right. Neither one of them is wrong. It's simply that what's simultaneous is relative, depending on your state of motion. And from that, Einstein easily figures out that time is relative, depending on state of motion. In fact, the paper he writes, The Electrodynamics of Moving Bodies, you should actually read it. It is a very readable paper, unlike most science papers. And in it, he says, he's trying to talk about simultaneity and talking about how you define, something happening at the same time and the passage of time. He says, what do I mean about time? It means that the light, when it hits from my watch to my eye and says it's 7, and the light of the train entering the station, reaching me at the same time, that sort of thing. So he says, if you can't define what's simultaneous, it means all time is relative, depending on your state of motion. Now, you're scratching your heads a little bit. Don't feel bad. In fact, if you have really tough questions about it, Lawrence and Arthur are there later to explain the relativity of simultaneity. But the rest of the physics community doesn't quite get it either. This is 1905. In 1906, he applies for about 12 jobs teaching high schools. Gets rejected in every one, even though he sends in that paper. He still can't get a job at a university. 1907 still didn't have a job at a university. 1908 still didn't have a job at a university. So the European physics community is slightly baffled too by these miracle year papers. One person's not baffled, a really interesting woman. Mileva Maric. Mileva Maric was a Serbian physics student, a young girl trying to make it in the world of physics and mathematics growing up in Serbia 100 years ago. And that was kind of hard, unlike being a woman at Harvard today, where it's easy to do science and math. In Serbia back then it was hard. You couldn't get into the Zagreb Academy. Her father's an army officer, gets her into the Zagreb Academy. And eventually she graduates very well in science and math from the Zagreb Academy and becomes the only woman in Einstein's section at the Zurich Polytech. Now, as you might suspect by seeing them together in this picture, they fall madly in love. So madly in love that the letters, some of them have been sealed up until last year. Their letters are filled with, Dolly, you turn my pillow on fire, and all sorts of passionate things. As students, they go hiking around Lake Como in northern Italy. She gets pregnant. They have an illegitimate daughter, Lazurl. They put her up for adoption in Serbia. After they graduate, they still can't get married because he doesn't have a job. Finally, the week he gets the job in the patent office in Bern, he, along with the people I showed you in the picture, Conrad, Michele, Maurice Solovine, as witnesses, they get married in the registrar's office in Bern. They have two sons. Hans Albert and Edward. And they have a very tumultuous relationship, as you might suspect. So tumultuous that even after she helps check some of the math in the 1905 Miracle Year papers, helps prepare them for publication, I don't think she should get credit for being a co-collaborator, as some people have asserted. If you look at all the papers, the concepts are basically Einstein's, but heck, she put up with Einstein during that period too. She deserves a lot of credit for that, but the marriage totally falls apart. They're fighting. That's what these letters under seal are about, custody of the kids, stuff like that. At one point, he has a contract that he offers her. Says, if you want to stay married to me, here's what you have to do. It's a one-page contract, and it's like, line after line. You'll bring my food to my office, my room. You will not interrupt me when I am trying to work on my projects, et cetera. New Yorker did a cartoon on it after my book came out because it was in one of the reviews of the book. And so it's like, Einstein being a total jerk. Fortunately, after thinking about it for a day, she declined to sign the contract. They decide to get a divorce. He can't afford a divorce. And so he offers her an amazing deal in the letter. He says to her, one of these days, one of those papers will win the Nobel Prize. If you give me a divorce, I will give you the money. Now, she's a scientist. She takes a week. She thinks about it. She consults with Fritz Haber, another scientist. She gets a lawyer and finally decides to take the bet. It's not until 1922 that they announce his Nobel Prize. But she collects the money and buys 3 apartment buildings in Zurich. Now, don't try this at home. It doesn't always work. In the meantime, Einstein's finally gotten an academic job, moved up the academic ranks, finally at the heart of theoretical physics, the Prussian Academy and the University of Berlin. They're having, there's a chapter in my book about the real fights he's having on custody of kids, fighting over who's going to pay for skis and the Christmas vacation. November 1915, letters flying back and forth about why he can't come visit for Christmas, why he's not going to pay the 50 Swiss francs it cost for the skis she bought, all these things. And those very weeks, it's amazing. I mean, his ability to compartmentalize and everything else. He's become a pacifist. He's the only person in the Prussian Academy opposing Germany's entry into World War I. And believe me, that is the definition of a nonconformist deciding to become a war resistor and pacifist in Berlin in November 1914. And what he's doing is trying to complete, in somewhat of a race against somebody else, the most elegant theory in the history of science, the general theory of relativity. Now, the general theory is called the general theory because, as I said, the special theory basically, to simplify a bit, only applies to constant velocity motion. As I said, if somebody's gliding along and you're gliding along, all the laws of physics apply. But if you're accelerating or slamming on the brakes or rotating, you kind of think, well, that's different. Coffee sloshes, balls bounce in a different way. The laws of physics seem to be different. Einstein really does not like special cases, does not like theories that apply only to the special case of constant velocity motion. Like a good artist, like a good musician, like a great scientist, he wants a unified theory. He wants a theory, a general theory, that applies to all cases of motion. So he's trying to generalize his theory to apply to accelerated motion as well. Secondly, his special theory of relativity had gotten rid of two great precepts of Sir Isaac Newton. Very first book in the Principia, Sir Isaac Newton tells us that time marches along second by second, irrespective of our observation of it. Einstein has thrown that out with the special theory. He says, no, time is relative, depending on your motion. Likewise, Sir Isaac Newton said space is absolute. It exists in its absolute way, independent of any observations of it. Einstein says no. Einstein, because in his special theory, says if you're speeding up, things get shorter. If you're trying to catch up with that light wave, you remember I told you he was trying to do that light wave, he realizes, yeah, no matter how fast you move, Maxwell's equations say the light wave will, in your frame of reference, keep moving at a constant speed, but time will slow down for you. That's the explanation of the 16-year-old's dilemma about the light wave. So he's thrown out two of the great principles of Newton, but Newton has another principle that's still standing, which is, of course, his theory of gravity. Newton's theory of gravity says that gravity is simply an attraction between two objects, an attraction that happens instantly at a distance, magically, for no apparent reason. The sun instantly attracts the earth at a distance. The earth attracts the moon at a distance, instantly, over time. Einstein says, no, nothing happens instantly at a distance. Nothing travels faster than the speed of light. Not even information travels faster than the speed of light. So Newton's theory of gravity, something has to be wrong with it. Once again, he approaches it visually with a thought experiment. A creative leap of the imagination, not some hard crunching of data from experiments or hard crunching of the math. Simply a thought experiment he does at his desk at one point, first in the Bern Patent Office and then later in Berlin. And the thought experiment, in its many guises, one of which is simply this. Imagine being in an enclosed chamber. If you have a bad imagination, walk outside, go to the elevator that Jeff Berkus built, be in an elevator sitting still in a closed elevator, resting on the surface of the earth. If you're there, what do you feel in an enclosed chamber resting on the surface of the earth? You're in a gravitational field, so you feel your feet being pressed to the floor. If you take something out of your pocket and let it go, it falls to the floor at an accelerated rate, right? Now imagine being in the same chamber, deep in outer space, where even Richard Branson has yet to go. Deep in outer space where there's no gravitational field. But the chamber is accelerating upward. Now do the thought experiment. What does it feel like to be in that chamber with no gravity, but accelerating upward? Your feet are pressed to the floor. You take something out of your pocket and you let it go, it falls to the floor at an accelerated rate. Einstein calls it the principle of equivalence. All of the local effects of gravity are equivalent to the effects of acceleration. It's actually not that hard to picture. We can picture it right here. Galileo should have figured it out at the Leaning Tower. We've all known since high school physics that the inertial mass of an object, meaning the force it takes to accelerate it, is always equivalent to the gravitational mass of the object, how much it will weigh in a gravitational field. But up until Einstein, nobody had fully explained why. Einstein says it's because gravity and acceleration are equivalent. There's an equivalence of the effects of gravity and acceleration. And from that, he's doing what he wants to do, tie in accelerated motion in his theory of relativity, put it all part of a theory of gravity, and he comes up with a theory of gravity that simply is that the gravity is the curving of space. What do you mean by that? He says, imagine an object, and imagine two dimensions first. For example, imagine a trampoline fabric in your backyard, and you take a bowling ball and you roll it on. What does the bowling ball do? It curves the fabric of your trampoline. It curves the fabric, two-dimensional fabric. Imagine you roll some billiard balls behind it. What happens? The billiard balls roll, and then they start curving, and they curve towards the bowling ball. Why? not because the bowling ball's got some mysterious attraction at a distance, the way Newton said, but because the bowling ball has curved the fabric and the billiard balls roll down the curve. Now, you and I can actually picture that. If you're Einstein, you can picture it happening in 3 dimensions, that an object curves all 3 dimensions of space. And if you're truly Einstein, you can imagine it happening in 4 dimensions, because what Einstein tells us is that the 3 dimensions of space and time combine into a 4-dimensional fabric called space-time. So he simply says gravity is the warping of the 4 dimensions of space-time. Now I'm looking at some people in the back, and they were nodding when the trampoline fabric was being curved, and now they're shaking their heads. All I can tell you is don't feel bad. This was November 1915, this amazing burst of creativity. As I said earlier, they don't give them or they don't announce his Nobel Prize to 1922. So you got a lot of confused people not quite sure whether relativity is philosophy, with all due respect to philosophers of science, or whether it's concrete, physics and stuff. And in fact, anti-Semitism is arising at that time, because at that time World War I is ending, Germany is losing, and the pacifists and the Jews are being blamed, and the internationalists. And if you happen to be an internationalist Jewish pacifist named Einstein, you're not in great shape. Young politicians like Hitler and Munich start writing about Jewish science and why it's different from Deutsch Physik, real German physics that's rooted in reality. And Einstein sort of feels this rising anti-Semitism in Germany when he speaks the anti-relativist movement coming up, partly based on that. And so what Einstein does is he comes up with a way you can test. He does that in all of his great papers. He deduces these wonderful theories from thought experiments, his imagination. But he said, if you want to test it, here's how you can do it. And so he says, one way to test whether my theory of gravity is right is if E equals mc squared, energy and mass have an equivalence, and gravity is the warping of space and time, then gravity will bend a light beam. And specifically, he says, how much, in his field equations of relativity, he describes how much gravity will bend a light beam. In fact, he says, if a light beam is passing from a distant star, the light is passing right next to the sun with the sun's gravitational field, he calculates that the light beam will be bent by approximately 1.7 arc seconds. He says, go look, you can see that I'm right. Problem with going to look and to see if he's right is you can't see the stars right behind the sun. When we know that, you go outside and look, the sun gets in your eyes. So they have to wait for the total eclipse of the sun to see if he's right. And in May 1919, there's a great total eclipse of the sun, just as World War I has ended, and a British Quaker pacifist named Sir Arthur Eddington decides that science transcends politics and hatreds and bigotries and biases. He's going to send an expedition, go personally on an expedition, to look at the May 1919 eclipse of the sun so he can try to prove the theory of a German Jewish pacifist. And so he sends an expedition to Brazil. He himself goes to an island off the coast of Africa known as Principe. They photograph during that 3 minutes or so of the total eclipse of the sun, the stars in the Hyades cluster behind it, to see if they seem shifted by 1.7 arc seconds. It takes a while to bring all the photographic plates back to England. But when they do, Sir Arthur Eddington calls a meeting of the Royal Society. J.J. Thomson, the discoverer of the electron, is in the chair. They point to the picture of Sir Isaac Newton in the Grand Hall of Piccadilly. People like Bertrand Russell coming down from Cambridge, because everybody knows this is a great meeting that's going to just have one item on the agenda. Was Einstein right? And they say, point to the portrait of Newton and say, forgive us, Sir Isaac Newton, your universe has been overturned. Now this was years ago, back, really a long time ago, back when the New York Times knew how to write good science headlines. You have to picture this. By the way, the New York Times doesn't have a science correspondent there in London, but they do have Henry Crouch. And nobody here, some of you may know who Henry Crouch was. He was the great golfing correspondent of the New York Times. There in England, covering St. Andrews, some other golf event. And so there he is. He's the only correspondent they have. They send him to the meeting of the Royal Academy. He has to interview Sir Arthur Eddington 3 times to get it explained to him. But then comes the headline that makes Albert Einstein the most famous celebrity scientist perhaps in history and one of the most famous people in the world. New York Times headline, "Lights all askew in the heavens." I love this headline. Men of science more or less agog over results of eclipse observation. Einstein theory triumphs, stars not where they seemed or were calculated to be, but nobody need worry. Back then, too, the New Yorker runs cartoons of people trying to figure out the theory of relativity. Einstein is suddenly the most famous sort of celebrity in the world. And he does something interesting because he's invited to represent Germany in the Solvay conferences, the European Physics Conference after the war. He's the only German invited, and it's bringing Germany back into the fold of scientists. Einstein's planning to go. And then he gets a call. Einstein had been raised in a secular Jewish family, hadn't really thought too much about, except for a very brief period in his youth, hadn't thought too much about his religion. But with the anti-Semitism arising, he had said, it reawakened my spirit of tribal kinship with the Jewish people. So he gets a call from Chaim Weizmann, the head of the World Zionist Organization, saying, come to America, raise money for refugee Jewish scholars, for Hebrew University. Einstein's never been out of Europe. And he does something that surprises everybody. He says yes. Decides to go on a fundraising tour across America for the World Zionist Organization, causing the other German scientists to be furious because he's skipping the Solvay conference to do so. But it's a new phase in Einstein's life. Not only becoming a celebrity, but using that celebrity for purposes, political purposes, something we see often today. But you have to remember back then, the notion of celebrity, the notion of publicity was abhorrent. There's a beautiful letter from Maya Einstein, right after that headline in the New York Times I told you about. Maya Einstein is the sister of Albert Einstein, and she's back in Zurich, and she sees in the local Zurich paper the headline of Einstein. She writes him a letter saying, I saw your name in the papers today. And you think she's going to congratulate him on his theory. It says, you must be appalled. How horrible it must be to be in the newspapers. I'm so sorry for you. I mean, because people did not like fame and publicity. Einstein has a love-hate relationship with his fame and publicity. When he arrives with Chaim Weizmann at the Battery in Manhattan, the newsreels have been touting him coming day after day. It was a big deal. 15,000 people are there to meet them at the Battery, the great celebrity. Weizmann gets off the boat first, and they ask Weizmann what they always ask people who've been with Einstein, which is, do you understand the theory of relativity? Weizmann says, on the way over, Professor Einstein explained it to me many, many times. And by the time we got here, I was convinced that he understood it. So, they parade him up 2nd Avenue, crowds lining up. I mean, I don't know about you all, but I don't know that many theoretical physicists now who get open-air parades up through the Lower East Side. He lectures all across the Midwest, Eastern United States, goes to Princeton, lectures for 4 hours on relativity. One of the students tells the school newspaper there, I sat way up in the balcony, but he spoke over my head nonetheless. Those of us who live in Washington we can fathom this. They bring Einstein to Washington. And so when he arrives, the Senate of the United States decides to debate whether relativity theory is true or not. For your science and politics thing, you should pick this up. Senator John Rankin of Mississippi in the opposition, Boyce Penrose of Pennsylvania, putting the entire theory in the congressional record, arguing in favor of the theory of relativity. They bring Einstein to see President Harding, and they ask Harding what they ask everybody, which is, do you understand the theory of relativity? That was a long time ago, as I said, back when politicians were honest, so Harding says no. And Einstein says it doesn't really matter because Einstein doesn't understand the theory of normalcy, which was Harding's political platform. Anyway, he becomes this huge celebrity. They even bring him out. He arrives for the opening of City Lights with Charlie Chaplin a few years later. Chaplin has a wonderful line when they're cheering as they arrive. They cheer you because they don't understand you. They cheer me because they understand me. But something interesting happens to Einstein. He wins his Nobel Prize. His quantum theory, that notion that light is both wave and particle, is evolved by the mid-1920s into a quantum mechanics that has uncertainty at its core. Einstein is not comfortable with that. There's one pillar of Newton's universe that Einstein still loves, which is what Newton calls strict causality. And Einstein wants to restore that notion of certainty. He repeatedly says, when confronted with things like the uncertainty principle of Heisenberg and Niels Bohr's idea that they're basically probabilities, not certainties, underlying the subatomic level, Einstein famously says repeatedly, I cannot believe, battery is fully charged, okay. I cannot believe that God would play dice with the universe. At one point, Niels Bohr finally says to him, Einstein, please quit telling God what to do. But Einstein's invocation of God, and I know some of you are skipping Sam Harris in the Greenwell Pavilion, so afterwards you can go hear him and get the balanced view of this. Everybody thinks Einstein, not everybody, a lot of people think Einstein's invocation of the good Lord is just a figure of speech. He does it often. He says that when I try to figure out a theory, I think of how the good Lord would have created the universe. And so, in fact, when he gets the telegram telling him that the eclipse observations have proven his theory, he shows it to a graduate student. She says, you must be thrilled. He says, no, I was confident. She says, yeah, but what would you have thought it had turned out the other way? He said, I would have felt sorry for the good Lord because the theory is correct. So people always thought he was just talking about the old one, the good Lord, just as a figure of speech. But as he turns 50, 1929, he starts writing much more about science and faith, science and religion. He writes one of us saying, science without religion is blind. Science without religion is lame. Religion without science is blind. He's at a dinner party at Berlin. They ask him, the hostess is stunned when somebody says that Einstein's religious. He says, yes, I believe in God. He said, I believe that there's a spirit manifest in the laws of the universe, a spirit in the face of which we must be humbled and awed. And that, to me, is my sense of cosmic religion. It was not a personal God. He did not believe in a God who would intervene and change the laws of physics or nature for you. If you prayed hard enough and intercede in our lives, you couldn't pray hard enough and say, well, make it a snow day tomorrow because I haven't done my homework or something. He said, for some people, miracles are evidence of God's existence. For me, it's the absence of miracles that are evidence of God's existence. The evidence is in the harmonies of the creation of the universe. At one point, Cardinal William O'Connell of Boston says, well, it still smacks of atheism because it's not an intercessional God that will intercede on our behalves. So Rabbi Maurice Goldstein, who was the head of the Reformed Jewish movement in New York, sends him a wonderful telegram that says, Einstein, do you or do you not believe in God? Answer 50 words or less. So Einstein doesn't use up the 50 words. He simply says, I believe in Spinoza's God, a God who is manifest in the harmonies of the universe. Now, that doesn't really satisfy the rabbi, it doesn't really satisfy the cardinal, but I think a lot of people, especially if you look at a scientist at age 50 wrestling with eternal questions, in which he says, yes, these are questions that are far too vast for my limited imagination, so that's why I feel humbled and awed when I address them. We can understand that sort of deism, the same deism that Benjamin Franklin or Thomas Jefferson and others get to. He also becomes has been very much a pacifist, but unlike other politicians, let us say, he believes there should be some correlation between your general theories and the actual facts. And so when the facts change and Hitler takes power in 1933, he suddenly says, I'm not a pacifist anymore. And says, if I were a young man, I would join the army. Sometimes it's necessary to resist. And he meets with his friend Leo Szilard after Einstein immigrates to America. And Szilard, who had been a friend of his, a scientist, who had come up with the concept of a nuclear chain reaction, at least in the tale, comes up with the concept while waiting for a traffic light in London. So comes to America, explains to Einstein the notion of a nuclear chain reaction, and they realize what the consequences of that could be. So Einstein, with Szilard, Teller, and Wigner's help, composed the most famous letter perhaps ever written by a scientist to a political leader. And it's from Albert Einstein, who's in Peconic, Long Island, because it's August 1939, to F.D. Roosevelt, the White House in Washington, explaining the notion of a controlled chain reaction and saying this new phenomenon could also lead to the construction of bombs. Franklin Roosevelt says this demands action, starts the Manhattan Project, building the bomb. One of history's ironies, Einstein had been such a pacifist that J. Edgar Hoover had collected dossiers, boxes and boxes on him, and he was denied a security clearance to actually work on the Manhattan Project. Making him, even though he loved America, he became an opponent of the Red Scare, McCarthyism, saying that it was free speech, free thoughts, free minds that led to creativity. There was a connection between free thought and creativity. That's why America was a creative place, but that's why America must always protect its free thought. Even though he didn't work on the Manhattan Project, he's associated in the public mind with the bomb. We kind of see the E equals MC squared on the mushroom cloud behind him when we think of the bomb. And so he dedicates himself to yet another cause, which is the cause of nuclear arms control and a sense of world peace. Becomes a leader in the movement for arms control. At one point they ask him, how do you think World War III will be fought? He says, I don't know. But I do know how World War IV will be fought if we don't do something, with sticks and rocks. And so that becomes another of his great passions. And of course, that notion of long live impudence, my guardian angel in the world, his ability to defy conventional thinking and to be a nonconformist continues to extend to physics. Because even after there's more and more evidence that quantum mechanics is right, and he keeps getting various proofs of it seem to be right, he continues to feel uncomfortable, saying that the quantum mechanical explanation of the universe with probabilities at its core cannot be a complete theory. And he says, and they say, well, and if you look at why he was against it, it wasn't just he didn't like probabilities or he believed in strict causality. It's because he was a realist. He believed there was an underlying reality, whether or not we could observe it. And the scientists like Bohr and Max Born, his friend, and others keep saying, but when you were young, you said, if we can't observe simultaneity, we don't know it exists. If we can't observe time, we don't know. You used to feel that way. You used to challenge every assumption, and that's all we're doing. We're taking a play out of your playbook. And he finally explained himself by saying, perhaps to punish me for my contempt for authority, fate has made me an authority myself. It's kind of interesting because I think, once again, at age 50, age 60, we all wonder, why are we less rebellious? Why are we less willing to challenge the conventional thinking? Why do we more often say, oh no, we've tried that before, it doesn't work and stuff? And Einstein wrestles with that in himself as well. He's offered the presidency of the state of Israel for his support for Israel. Einstein, as I hope you've determined by now, is a very smart person, so he says, no thanks. I did read, I was looking in the archives, and he's there with Ben-Gurion in that picture. Ben-Gurion was the prime minister who offered him the presidency. There's a note from Ben-Gurion to Abba Eban, some of you may have known him, was UN ambassador here at the time, saying to Abba Eban, I've offered him the presidency, but let me know, what am I supposed to do if he accepts? So I think they both knew he was supposed to turn it down. But he did agree to write a speech for Israel Independence Day. And even to the very end of his life, 1955, he has an aneurysm. It bursts. It's hemorrhaging. He decides not to get an operation. His time has come to die. He's brought to the hospital. He does the things that still concern him. He signs the Bertrand Russell Albert Einstein Manifesto calling for world peace in the nuclear age. He decides to write the first sentence, is all he can get out, of the speech for Israel Independence Day that he knows he'll never be able to deliver because he's dying that day. And he just writes the first sentence, and he had told Ben-Gurion that he didn't want to write about Israel or Judaism. He wanted to make it a broader speech about the need for world peace. So the first sentence is, I speak to you today not as a Jew and not only as an American citizen, but as a human being. And then it trails off a bit. You see, he puts it aside as the pain becomes too great. But later that afternoon, he revives a little bit, reaches to his nightside table again, pulls off a piece of paper. This time it's not the speech, but it's a few pages of calculations. Still, trying to get that field equation. When he looked at the compass, trying to figure out field equations, can explain it all. Trying to get that field equations, the unified field theory, whatever it could be, that he'd been working on now for 25 years, somewhat fruitlessly. Other scientists making fun of him. But he still thought that maybe he could get us closer to that field equations, the unified field theory. So he starts writing equations again. Line after line, tightly scrawled equations. I went to Hebrew University just so I could actually see the actual page and touch it. And there it is, the very last page he writes. Line after line of tightly written equations with all sorts of little mistakes that get crossed out. Even arithmetic, mathematical errors crossed out and fixed. Until finally at the end, he writes one last line of equations. You can see it starts to dribble off the page until he goes to sleep for the very last time. One last line of equations that he thought would get him and the rest of us just one step closer to that spirit manifest in the laws of the universe. And so that's how a very impertinent and rebellious but unbelievably creative third-class patent clerk became the mind reader of the creator of the cosmos and the locksmith of the mysteries of the atom and the universe. Thank you all. We have 15 minutes, and Lawrence Krauss and Arthur Miller are here to answer any questions you have. And they're not allowed to ask questions because they'll say, well, you weren't exactly right about the frame of reference in Maxwell's equations, but I did the best I could with their help. Oh, Lawrence, you're the first, you jerk. All right. Okay.
Einstein had made the wrong calculation.
There's all sorts of little wonderful ironies in this. Einstein, in his theory, I think we sometimes call it the Zurich notebook theory or the Entwerf. He called it the outline theory. He actually has it wrong the first time he tries to do the field theories of gravity. And what he would have given was something sometimes called the Newtonian answer, which is about half of the deflection. And I won't get into all the reasons why, but he basically doesn't have the geometry of the curvature of the universe done yet, because he's not good at geometry, believe it or not. So anyway, he comes up with it, and he convinces Freundlich, I think Erwin Freundlich was a young astronomer at the University of Berlin, that he has to go measure the eclipse of 1914, measure the eclipse, and prove Einstein right. Now, the problem is, if Freundlich had done so, Einstein would have been proved wrong. It would have really hurt him. So Freundlich goes off, and that eclipse of 1914 was most visible in the Crimea. Einstein refuses to join the Royal Academy in the University of Berlin unless they'll pay for this expedition. He comes there, becomes a pacifist. They get into World War I. Freundlich goes off to measure it. The Russians come marching into the Crimea, and there's a bunch of German scientists with all these telescopes about to picture the eclipse, and so they get taken prisoners of war, and they can't measure the eclipse. And the irony, but also the good news, is Einstein is spared being proved wrong, and there's probably some philosophy of science in there, but I don't know what it is. Yes, way in the back. He was, the question is, did he feel like a failure because he couldn't get the unified theory? I think there are about 12 different major approaches he does, from affine connections to, by the way, to different, as Lawrence has written about, different dimensions, which in some ways ties in with what the mathematical formalism of string theory. But he never really keeps throwing them away, as it doesn't come up right. They ask him, do you feel bad that you're wasting your time doing this? He says, no, somebody's got to pursue this. I've already made my reputation. I'm already famous. It's too dangerous for a younger scientist to be doing it. They could squander their whole career. I feel comfortable pursuing it. And I write about that some because there's some beauty in pursuing a theory, just the pursuit. Especially of a theory that would be so elegant and beautiful that would pull together all the forces of nature. Even if people at the time thought, well, wait, we're discovering more and more forces, more and more particles, it's getting less unified, but still that quest is a beautiful quest, even if it was a futile quest. And you can make fun of it, but I think it's going to take us 100 years or so. And 100 years from now, somebody actually finds, whether it's quantum gravity or string theory or whatever it may be, that there is a unified theory that ties things together. Maybe his quest won't look so ridiculous. Arthur.
Yes. Preface my comment.
Yeah.
Preface my comment by saying that
They'll turn it on for you. Yes.
I have a great deal of admiration for your book. What Walter has done is to bring all of Einstein's studies up to date and include what has been done, including the new letters as well. And it's written in a wonderfully perky style.
Thank you.
Many, many stories that are almost gone by this time. But Walter's book brings them to life with a wonderful ending. I believe that you said the ending to your book is the ending of your
Yeah.
lecture. With respect to the unified field theory, I think you also brought out nicely that Einstein really worked himself into a corner to the extent that he was only working on the unification of gravity and electromagnetism.
Right.
And that's all.
Then we discover the weak force. Yeah.
Figuring that once he somehow or another made progress with just those two forces, there would be a way to include others. But it was a dead-end situation.
Yeah, and people ask me, was he, right or wrong? And I say, well, thank goodness my book ends when he dies in 1955. Other people have to figure out where the, quantum mechanics particle theory has taken us. I'll end with this, with notes about the fact I'll go over and do a book signing. I think I'm doing it in 15 or 20 minutes over there. But Arthur Miller has two books out. One is Einstein Picasso, which truly looks at something to me as very interesting. And I actually keep referencing the book and telling people to buy his book when they ask me about it, which is something amazing happens in creativity in 1905 to 1915, let us say, as modernism is born. And you see Einstein talking about relativity, breaking the classical bonds, but you see Stravinsky and Schoenberg breaking the classical bonds in music, Proust and Joyce talking about, playing with time and reference, and of course Picasso, Kandinsky, and others doing it in art. And what is it about that period? Arthur's book takes the 1905 theory of relativity and the 1907 painting Damoiselle d'Avignon of Picasso, and talks about Poincaré and others who had been playing with the notion of time, how it all reverberates. We should look at that period of 1905 to 1915, an explosion of imagination and creativity in all fields, art, music, science, literature, poetry, novels. And why did that happen? Why were people able to question the classical bonds and think of new ways to write novels, write music, write science? And we don't have that now. If I may say so, it's hard to judge as a historian what people think 100 years from now. This period is not one of the most creative periods, whether it be in reinventing novels, music, or science and stuff. No great leaps. And so hopefully we'll again enter into a great creative period. One of the weird things about Einstein's theory of general relativity is that if you look at the field equations of general relativity, beautiful, beautiful equations, something mysterious happens, which is they can result in what you might call a singularity, that gravity can bend in on itself in such a strange way that nothing could escape, according to the equations of gravity. Einstein thought that was just some quirk, I think. You may have to correct me, that somehow people would figure out how to accommodate that it couldn't really be true. But then, of course, Kip Thorne, John Wheeler, many other people in your latest book realized there are black holes, that this is the purest manifestation of Einstein's equations of general relativity. So his second book is Empire of the Stars, right, which is about the rivalries and friendships amongst the people who understood black holes. And Lawrence Krauss, whose books, all of their books are over there, did Light in the Mirror, which among other things, he's doing many books, explores the notion of multiple dimensions, which is at the core of some of what Einstein did, and especially at the core of special relativity. And if you don't understand special relativity in my book, he and Brian Greene both have really clear explanations of special relativity. So anyway, I'm happy to answer some more questions informally, but I am going to wander over to a book signing over at Pepke, but maybe Arthur and Lawrence, their books will be there as well. Thank you all for coming.